All right, so I've already talked about how big the TDTR signals you expect to see are if you're just using a biased photodiode. And the biggest you might ever expect to see them might be something like 10 microvolts. If you have a 1 Kelvin temperature fluctuation that you're trying to detect, and if you're using the largest possible probes signal. In reality, a lot of times that number is a lot smaller, either because you can't generate temperature fluctuations that big using your current laser, or just because the probe signal is smaller, or the thermoreflectance of the transducer that you're using is smaller than for aluminum if you're not using aluminum. In a lot of systems, you just don't get that much signal. And so almost all the TDTR signals that I've seen, every TDTR system that I've seen uses some sort of amplification after a biased if they're using a biased photodiode, the way that I had shown before. And what that amplification looks like is different on different types of systems. So some groups will just automatically go to a actively amplified photodiode. So you can buy amplified photodetectors. I'll talk about those as a separate thing because they have their own sort of separate behaviors. But a lot of groups, including the first group who invented TDTR, or at least widely used it, David Cahill, they sort of developed this technique that uses passive amplification to essentially noiselessly amplify photodiodes. Another way is to actually have a separate preamplifier, and I'll talk about that separately. In this slide, I thought I'd talk about the fun trick that you can use to do pretty much noiseless amplification of a TDTR signal. So the fun trick that works with biased photodiodes is to use something called a resonant filter. And that's a fancy name, but actually all it really is taking your normal photodiode circuit. Let me go back here. So in a normal photodiode circuit, which I hadn't shown previously, a pretty good effective way of thinking about the circuit that's inside of your photodiode. Your photodiode is shown inside this yellow box. It's basically an alternating current source, which is basically the junction that's converting the light that you're sending in to a current, plus some built-in capacitance associated with that junction. And typically at least an approximation of that capacitance comes as a specification with your biased photodiode. So for example, things with a large capacitance will have slow response times, and things with a small capacitance will have fast response times. So the high-speed things that we're using generally have a very small capacitance, but it is finite. And then externally, what you actually see when you operate these things is basically like a BNC connection, typically like a BNC cable connection, which is just the connection that you'll use to send the signal to either your lock-in amplifier or to a preamplifier if you're using one. And inside either the lock-in amplifier or the preamplifier will be across the two terminals, there's usually a 50 ohm resistor that you're actually passing the photodiode circuit through. Okay, so that's basically how a normal photodiode circuit works. I'm sort of hiding the biasing, but this is a good way to think about it. Okay, so the trick that was developed by the Cahill group when they invented TDTR, which still works today in most situations, is that you can just add an inductor to that circuit. So like before you send your signal to the lock-in amplifier or preamplifier, what you'll do is you'll typically have like a little box, and inside that little box is just an inductor. Why do you put that there? Well, I think the trick is sort of hidden in the title for it. So it's called a resonant filter. Why is it called a resonant filter? Well, okay, let me pull up my my handy-dandy laser pointer here. Okay, so inside a resonant filter, if I look at this circuit, what I have is, I have an external current that is exciting this circuit, but it's an RLC circuit, meaning that it has a resistance, an inductance, and a capacitance associated with it. I know probably many of the people looking at this are mechanical engineers or come from a non-electrical background, so let me explain it like this. an inductance is basically inertia for charge. That's basically what an inductor is. It creates inertia for the flow of charge. Resistance is basically damping of charge flow. And a capacitance is a storage mechanism, sort of a lot like a spring is a storage mechanism for mechanical systems. So you have something like a spring, an inertia, and a damper. So it's basically a mass spring damper type arrangement that is being excited sinusoidally. And what do we know about mass spring damper systems that are excited sinusoidally? Well, what we know is that they resonate, or at least at certain frequencies, the amplitude that of whatever the quote displacement is can blow up. And guess what? That happens in this system too. So you're exciting with an AC current, which is sort of like a alternating forcing function for the circuit. So you're basically exciting it with at something at a particular frequency, and yeah, the voltage across this terminal that goes across the resistance blows up, basically compared to its non-resonant counterpart. And so if you operate this circuit at a particular frequency, meaning that if the signal that you are collecting happens to be oscillating at exactly the right frequency that corresponds to the resonant frequency of this RLC circuit, then instead of just getting the normal voltage that you would expect to see across this resistor, you'll actually get one that is way, way bigger. It turns out that this circuit does not blow up to infinity because the resistance adds some damping. So a damped resonant system does not blow up to infinity, but it blows up to a large number. But you get a very large voltage output for a relatively small current that is being put through at the junctions of this capacitance. And so just by adding a small inductance, you can cause the voltage to increase. Like if you're, typically what you observe is if you're designing a TDTR system that uses an electro-optic modulator that operates around 10 megahertz. So the 10 megahertz is chosen to be a high speed. So if I choose inductance to add to this resonant circuit that makes the resonant frequency be about 10 megahertz, then I can get enhancements in the voltage that are on the order of tenfold, maybe even a little bit bigger than tenfold, around 10 megahertz. And so that process, that's called the quality factor of the circuit. And the resonant frequency can be at least estimated using a relatively simple to use formula. So, for example, I have it sort of written on here on the bottom. If you buy a biased photodiode, and typically that the manufacturer will tell you the capacitance of that junction, so you'll typically know the value of C, then you can choose the value of the inductance L that gives you a resonant frequency approximately in the right area that you're looking for. And so, if you make a little box that has an inductor in it, you will get this sort of free amplification before your signal goes to your lock-in amplifier or your preamplifier. And so this is typically what we do. The only downside to doing this is basically that you can so once you have this inductor hooked onto your photodiode, then you can only do the experiment at that frequency. And so one of the times when you would not want to do this is if you're going to be changing frequencies all the time. And the other situation, so I'm showing the amplitude of the amplification. There is another issue to consider, which is the phase of the signal. The phase tends to change quite steeply in this area, and so if you have a lot of sensitivity to phase noise, then or phase uncertainty, then using a resonant filter can make that worse. And I'll talk about some ways to get around that later in some more detailed stuff. But this is generally what people do. Many groups are using these resonant filters to get large amplifications that are essentially passive and don't introduce any additional noise beyond phase noise. Okay, so that's one thing that people do. The next thing I'll talk about is the use of a preamplifier.